You trust your eyes. You trust reality. If you throw a ball, it follows one path. If you drop a coin, it lands in one place. Everything in your everyday world behaves predictably, solid, definite, certain. Physics worked like that for centuries. Then scientists began studying particles smaller than atoms, and suddenly reality stopped making sense. Imagine firing tiny particles, one at a wall, with two narrow openings. Behind the wall sits a screen, waiting to record where each particle lands. Simple setup, simple expectation. If particles behave like tiny bullets, they should pass through one opening or the other, creating two clear bands on the screen. But that is not what happened. Instead, the particles created an interference pattern, the same pattern produced by waves moving through water, bright bands, dark bands, peaks, and gaps. Somehow, these tiny particles behaved like waves, spreading through both openings at the same time. That alone was strange enough. But the real shock came next. Scientists decided to observe which opening each particle actually traveled through. The moment they measured the particle, the interference pattern disappeared completely. Suddenly, the particles behaved normally again, like tiny objects choosing one path only. Think about how disturbing that really is. Simply watching the particle changed the result of the experiment. Observation itself appeared to alter reality. For the first time, physics faced something terrifying. Particles did not seem to have definite positions before measurement. Until observed, they behaved like possibilities instead of objects. And that single discovery shattered the comfortable picture humans once had about how the universe works. According to classical physics, this should be impossible. An object cannot travel through two openings simultaneously. A coin cannot land heads and tails together. Yet every experiment kept confirming the same unbelievable result. The deeper scientists looked into the quantum world, the less reality behaved like a machine, and the more it behaved like a mystery uncovered. Scientists could accept particles behaving like waves. Strange things happen in science all the time, but one question refused to disappear. Why did the particles suddenly behave differently when somebody tried to observe them? To understand the problem, imagine a spinning coin hidden beneath your hand. Before you look, the coin is not useful to you as heads or tails because you do not yet know the outcome. Quantum physics pushes this idea much further. According to the mathematics, a particle can exist in many possible states simultaneously until measurement forces one result to appear. This bizarre condition is called superposition. An electron inside the double-slit experiment does not seem to travel through one opening secretly while fooling the observer. Instead, it behaves like a cloud of possibilities spreading through both paths at once. The interference pattern appears because those possibilities interact like overlapping waves. Then observation changes everything. The moment scientists place a detector near the slits, the electron suddenly behaves like a normal particle again. One path, one location, one outcome. The wave of possibilities collapses into a single measurable reality. But what counts as an observation? That question terrified physicists. Does the particle somehow sense the measuring device? Does information itself alter reality? Or does the universe remain uncertain until interaction forces a decision? Even today, scientists debate what quantum measurement truly means. What makes this even stranger is that quantum superposition is not theory anymore. It is experimentally verified fact. Modern technologies already depend on it. Quantum computers exploit particles existing in multiple states simultaneously. Lasers, semiconductors, and magnetic resonance imaging all rely upon quantum mechanics working exactly as predicted. Yet nobody fully understands why nature behaves this way. In classical physics, reality exists independently of observation. A planet still moves through space whether anyone watches it or not. Quantum mechanics challenges that assumption completely. At the smallest scales, particles stop behaving like tiny objects and begin behaving like probabilities waiting for reality to choose a final answer before our eyes completely. At this point, quantum mechanics stops feeling like physics and starts feeling like philosophy, because if particles can exist in multiple states before observation, then what does reality actually look like when nobody is watching? That question has haunted science for more than a century. Some physicists believe the particle truly exists in many possible states simultaneously until measurement collapses everything into one result. Others argue that every possible outcome actually happens in separate parallel realities. According to this interpretation, the universe constantly splits into countless versions of itself every moment. And the disturbing part is this: the equations work either way. Quantum mechanics remains the most accurate scientific theory humans have ever created. Its predictions match experiments with astonishing precision. Every smartphone, computer chip, laser, and advanced medical scanner exists because quantum physics keeps proving itself correct. The strange behavior is not imagination. Nature genuinely behaves this way. But the human brain struggles to accept it because our everyday experience evolved in a world of large objects, not quantum particles. You never see a football existing in two places at once because quantum effects disappear at larger scales. The weirdness hides beneath reality, invisible until scientists examine matter at incredibly tiny distances. Yet underneath everything around you, the quantum world never stops operating. Every atom in your body follows these laws, every beam of light, every chemical reaction. Reality itself is built upon probabilities, uncertainty, and invisible quantum behavior occurring constantly beyond human perception. For centuries, humans believed the universe behaved like a giant machine, predictable, definite, certain. Quantum mechanics shattered that picture forever. Particles can exist in multiple possibilities before measurement because reality, at its deepest level, may not be fixed until interaction forces it to become real. And that means the universe is far stranger, far less solid, and far more mysterious than human intuition was ever designed to understand completely.